then LP of F to equal to the collection of all. We define LP of F to be equal to the collection of all sequences Sn n equals 1 to infinity, so that for any n in the set of natural numbers, Xn is in F, and summation n equals 1 to infinity of valuation of Xn raised to power p is what? Is finite. We have to be very careful here. I use the word valuation because that has to do with the field. If F is the field of complex numbers, then this symbol, this represents the modulus of the complex number Xn. But if F is R, this represents the absolute value, for instance, the absolute value of Xn. So that is what we call the square space LP over F. Then for P equals plus infinity, for P equals plus infinity, we have L infinity of F to be equal to the collection of all Xn n equals 1 to infinity, so that for all n in the set of natural numbers, Sn is in F, and then the modulus or absolute value of Xn is less than or equal to k for some k greater or equal to 0. For some k greater or equal to 0. So what this means is that L infinity of F is the collection of all those bounded sequences in F. Y LP of F is the collection of all those sequences in F, so that this inequality holds. And if you look at it, you will find out that LP of F for P between 1 and infinity is the proper subset of L infinity of F.
Yes.
Anyway, which I demonstrate that because for this to hold, it means that the term of the series goes to 0. And going to 0 means that Xn goes to 0, and therefore Xn is bounded. So any sequence that is LPF is a bounded sequence, and hence in L infinity. And we know that there are so many bounded sequences, which those terms are not summable.
Yes. Okay.
There are so many bounded sequences, those terms are not what? Summable. The absolute value of the power will not be summable. Examples are that, meaning that this contains more elements and more sequences than this one. Let me make this remark. Throughout our discussion, the vector spaces will introduce the notion of nonlinear space, and the vector spaces involved will be vector spaces over the field of Riemann. For that reason, in this case, I will be writing, instead of writing LP R, I would prefer using LP. Just a notation for convenience.
Okay.
Instead of writing this, if I write, I'll be using this symbol for LP. We shall be using LP instead of LP of what? Of R. So when I say LP, you know that the sequence is coming from what? It's coming from the set of Riemann. Observe that if S bar equals Sn and equals 1 to infinity, and y bar equals Yn and equals 1 to infinity, we define x bar plus y bar equal to Sn plus Yn and equals 1 to infinity. Lambda in R, we define lambda x bar equals can be shown that LP is a vector space over the field of what? Over the field of polynomials, over R. Consider the sequence n equals 1 to infinity, given for all n in the set of natural numbers by Sn equals 1 over n. Then that sequence Sn n equals 1 to infinity. Let me say 1 over n equals 1 to infinity belongs to LP for P bigger than 1. That is for 1 less than P less than or equal to plus infinity. This is because for 1 less than P less than plus infinity, that's for P in this range. Summation n equals 1 to infinity of absolute value of 1 over n, the power, is equal to summation n equals 1 to infinity of 1 over n raised to what is. AP series. AP series with P greater than 1. Greater than 1. Thus what happens? Thus summation n equals 1 to infinity of 1 over n raised to power P is finite. This implies that this is equivalent to summation n equals 1 to infinity of absolute value of 1 over n to power P is what? Is finite. So 1 over n equals 1 to infinity belongs to what? LP, where P lies between 1 and what? And plus infinity. Moreover, for P equals plus infinity, we have that 1 over n equals 1 to infinity belongs to L infinity, since the sequence 1 over n equals 1 to infinity is what? Is bounded. Alright, since this sequence is such, is bounded. Thus is supremum n greater or equal to 1 of 1 over n which we know is 1. 1 is the supremum, is what? Less than plus infinity. Less than infinity. The boundary is supremum is less than what? Infinity. And therefore that sequence belongs to what? L infinity. The fact that this summation is finite makes the sequence to be in what? In LP, or P between 1 and the what? And infinity. So that's one example of a sequence that belongs to LP. And with this idea, you can check several sequences you've come about to see which and which belongs to which of the LPs. The sequence 1 of this sequence does not belong to L1.
Yes.
It does not belong to L1 because summation, let me say here that what 1 over n equals 1 to infinity. However, does not belong to what? L1, since summation n equals 1 to infinity of absolute value of 1 over n, which is summation n equals 1 to infinity of 1 over n is equal to what? Plus infinity. This is plus infinity. It's a harmonic series. That the sum is plus infinity, and therefore not finite. So it does not belong to L1. So that's one example. Then this is for when the infinity is excluded, and this is what I looked at. And I found that so for the fact that this is a P series, the series converges, and meaning that this is finite, and therefore this belongs to LP, whatever P satisfies that condition. Are you with me?
Yeah.
Then you take care of where P is infinity. When P is infinity, you use the fact that this is what? A bounded sequence. Together the supremum will be what?
Which is an element.
In fact, the supremum is what?
Is
Less than infinity. That makes it to be an L infinity. But your heart is not in L1. That's why you see that one. Yes, it's not in L1 because what? This sum is what? Infinity. It's a harmonic series that doesn't go on.
So, Prophet, so LP is the collection of sequences that converges.
Collection of, no, look, LP is the collection of those sequences. So that if you take the absolute value of the terms, and take the V power of the absolute value of the terms, and you consider the series, if the series is finite, then the sequence is in LP. Do you understand?
A series being finite now means that the term converges.
If the series is, when I say series finite, I mean if the series is convergent. But be careful here. We have to be very, very careful, please. Be careful here that when I take absolute value, I'm not looking at a kind of example of what non-negative series of non-negative terms. In that particular case, by convergence, we mean that the sum is less than what? Infinity. I hope you're following me. It's not like that is convergence of series. A series, and you say summation is less than infinity, does not necessarily mean that that series is convergent, because there's possibility that the series is that the sum is what? Minus infinity. So, but if it's a sequence series of non-negative terms, then to say that it's less than infinity is enough to Then there's another thing you raise, which is very important. It does not mean that every convergent sequence is in LP. It does not mean that every convergent sequence is in LP. Convergent sequence. Because you can get a convergent sequence. For instance, you can get a convergent sequence. This one goes to 0. But the series does not what? Converge. Meaning that this is an example of a convergent sequence, which is not, for instance, in L1. It's not in L1. Are you with me?
Yeah.
Fine. Now, looking at this, you can use it to play a lot of logical manipulations that will give answer to the question you raised. For instance, asking me to give one that is in L1, but not where? but not if that is L1. Fine. It's just a kind of logical manipulation. Watch what I'll do now. Using the same, that is borrowing idea from what we just generated. I'll get one that is in L1.
Okay.
See that my practice is not that so variable. It's a matter of applying the equal logic to this. Once one is given, from now on you can generate a lot of good ideas. For example, we can consider the sequence xn n equals 1 to infinity of three numbers. Given for all n in the set of natural numbers by Sn equal to 1 over n squared. What is it? 1 over n squared. Then the sequence Sn n equals 1 to infinity belongs to L1. Belongs to where? L1. Since watch. Since summation n equals 1 to infinity of absolute value of Sn 1 is P.
Okay. Yeah, peace.
1.
Peace.
You get what I'm talking about? Is equal to summation n equals 1 to infinity of 1 over n squared.
Yes.
Do you see?
Yes.
And this is what? Finite. Why? Because is the reason with p equal to 2. Therefore, this sequence belongs to L1.
And what does it? So 1 over n or is power of 2.
Then
1 over n absolute value or is power of 2.
which one?
He said to it
1 over n all raised for.
Fine.
Yes.
But what's the sequence? The sequence is this one. Therefore, that is raised to power 1 means this one raised to power 1. And that. Do you see the trick? Okay, watch this one. Another example. Another example. Consider the sequence xn n equals 1 to infinity of real numbers given for all n in the set of natural numbers by Sn equals 1 over root n. What is 1? 1 over root n. And then, watch. Xn n equals 1 to infinity is not in L2.
Yes. It's not in L2.
In L2.
Yes. Yes, not in L2.
Not in L2. Wait,
Not in
hold on.
L2.
Yes.
It's not in L2. Huh?
Why?
Since summation n equals 1 to infinity
1 over 2.
of absolute value of Sn raised to power 2 is equal to summation n equals 1 to infinity of what?
Absolute value of 1
1
over
over root
root n. Okay.
root n
Raised bottom.
raised to power 2.
Yes.
And what is this?
1
This
over
is
n. 1 over n.
This is nothing but summation n equals 1 to infinity of what? Of 1 over n, which is what? Which is constant. And therefore not finite. Do you see? Now once one is created, it gives room.
Yes.
And that is why I kept on advising students on the need to solve exercises.
Exercises, yes.
Every exercise is a method for a problem that is coming in future. So what mathematics is free of exercises. And then to me, it's no longer mathematics. One must spend quality time doing those things. And that is why it's good to start early. Because there's a way, a stage you get to sit down and do those things will be somehow boring.
Yes.
You somehow boring. But when you look at what the volume of work to be done, and you look at what faces you in the future, you may be forced to say, let me forget about this once and continue. But there's no way you can move forward if those ones are not first of all taken care of. That's one thing about this mathematics. One has to do people like this to see how to come out of all these things.